Hello people, and welcome to another video of Programmer's Corner. In this video we'll take a look at how to implement heap sort both recursively and non-recursively. But before we go into the implementation and the execution of it, let's take a look at what are the data structures required. So heap sort uses binary heap data structure and is a comparison based sorting algorithm. Much like selection sort, it also takes the first element, which is after a bunch of iterations, it takes the first element, which is the largest element in the given heap, and it swaps it with the last element, which may or may not be the smallest element in the given heap. Now let's take a look at what is a binary heap. A binary heap is a complete binary tree which uses two sorting techniques. The first technique is called a max heap and the second is called a min heap. Now in a given algorithm, in a given heap sort algorithm, you can only use one of the two techniques. You cannot use both of them. Now we'll take a look at it when we implement this. A complete binary tree. A complete binary tree, which the binary heap uses, is a binary tree where every level except possibly the last level is completely filled. So as you can see, there are no in between where a level is incomplete. Now again, this structure will only make sense if you put all these elements in an array. So if you take a look at, if you turn this into an array data structure, you have this as the first element, second, third, fourth, fifth, sixth, seventh, 8, 9, 10, 11 and 12. Now array being, it starts from 0, you can take 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And again, if you look at the way a binary tree is sorted, you can say, you can do it as, this is the 0th position, this is the first position, and this is the second position. So 0 times 2 plus 1, that gives you this, and 0 times 2 plus 2, that gives you this. Then if you go here, you have 1 times 2 plus 1, that gives you this, and 1 times 2 plus 2, that gives you this part. That's the fourth index. The same way, 2 times 2 plus 1 gives you the fifth index, and 2 times 2 plus 2 gives you the sixth index, and so on and so forth. And since the size of this is 12, if you go here, it's 2 times 6 plus 1 gives you what, 13. But there is no element beyond that because the size is 12, so this here is the last element. So as you see, every level is filled and all the nodes go as far left as possible. Now let's take a look at what is a max heap and what is a min heap. A max heap is a max heap is a sorting order in which the sort is from top to bottom. So if you take our root class, or if you take the root node in a tree, that root node in a max heap is going to be the largest node in the entire tree. But that doesn't mean that the last node is going to be the smallest node. As you can see here, this is the smallest node, but this is the last node. So if you want, and now max heap is also used in ascending, to sort a given array in ascending order. And that's why I said, when you use max heap, when you want to do a heap sort, we do a comparison based sorting order, and it's same as selection sort, where once the first iteration of max heap is done, you take the first element and you put it at the last element, because you swap it with the last element, because we know that is our largest element in the given heap. There is no other large element larger than that. But that can't be said by looking at this, at the max heap. That can't be said. The same thing cannot be said about the smallest element, because that's not always guaranteed to be the last element. So now this is a max heap where if you take any node, its children node are going to be lesser than or equal to that given node, and the same is true throughout. If you take max heap, for example. The other one is min heap. The min heap is the exact opposite of max heap. So if you take any given node, its children node are going to be its children node are going to be greater than or equal to the given node. So if you want to sort an array in a descending order, all you need to do is run a couple of iterations and sort this array using min-heap property. So at the top you get the smallest element. There is no element smaller than that in the given array. That's guaranteed. But that doesn't mean that if you take this and if you try to find the largest element, if you take the last element, that's going to be the largest element. That's not guaranteed. But here the top element is going to be the smallest element. That's guaranteed for sure. So you swap it with the last one, and you reduce the size by 1. There is the size of the heap by 1, and then you again run the min heap, and then we will see that you'll find the second smallest, and so on and so forth. So now, after finding that, now we know that what's a min heap, what's a max heap, and what's a min heap, what's a complete binary tree, what's a binary heap, and how binary tree is used using the properties of max heap and min heap. So let's take a look at the implementation of this. Now that we have seen what we require or what we need to know before we jump into heap sort, let's take a look at the implementation of heap sort. So to begin with, we have this array of about 10 integers, and what we're going to do is first we are going to turn this array into a tree. So to start, let's start working on that. So we have 10 here, we have 52 and 4 here, then 52 children would be 9 and 20, and 4 children would be 44 and 11, 9th child would be 3 and 8, and 20th child would be 12. So as you can see, we have 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. So as we stated before, our current is going to be I. So I right now is 0, and the next child is going to be I times left, or I times 2 plus 1, and we have the right child is going to be I times 2 plus 2. So knowing this, for the first iteration, for the first couple of iterations where we first run the algorithm, what we need to first do is we need to take the element at the second last level. So what we do is we take the size of this array and we divide it by 2. That is, right now it's 5 minus 1. So we take the fourth element. So 0, 1, 2, 3 and 4. That's the second last element with a known child. So we take that and we check if this element has a child and if this element is bigger than its child. Oh, sorry, if this element is smaller than its child. So right now what we're going to do is we're going to use the Max-Heap property, and what the Max-Heap property states that after a bunch of iterations, or after this first iteration, the top element of this heap is going to be the largest element in the entire heap. So now that we are sorting this array in an ascending order, what we do is we take 20. So while we do it, let's write this down. So for I equals n by 2 minus 1, this would be 2i greater than equal to 0. So what we do here is we have I is equal to n by 2, that's n is the size of the entire thing, that's 10, by 2 is 5, minus 1 is 4, so we start from 4, and in this what we do is we heapify. So we run a heap algorithm where we check if my current element here is gonna be, where actually I pass in my current index, that is I, then I pass in what's the end of it, the end of it, and then I pass in the array that I'm trying to sort. Now let's look at the Heapify function. So now I have, and here I'm going to do it first recursively, and then we'll do it recursively, which will be more easier. So we have the start point, we have the whole thing, and then we have the array. So what happens here is, before we jump in, let's take a look, let's note these down. So we have the current is I, the left, which is current times 2 plus 1, and then we have the right, which is current times 2 plus 2. So now that we have these, we know what's my left child and what's my right child. So what we do here is, so now we check is, if my left is less than n, and let's say my array of left is greater than my array of n, that means that I'm right now at 20, so the child of 20, if that child is greater than 20, then I need to swap it. I set the current to be left. Actually it's not that, it's actually current. Not that. So I have done that. Now if my right, if I have a right, if my right is less than n, and if my array of right is greater than array of current, let me do this. In that case, I also say current is equal to right. So now that, if you see here, if this if statement has been executed, then it comes here and it checks if there is a swap. So if I take a 9 for example here, let's say assume that there are two elements greater than 9. Let's say we have 9, we have 15, and we have 20. So we come here, we first see 9 and 15. Alright, there is a swap. So I say my current is this. But then I say 15 and 20. But now my 15 is bigger than 20, so I get to 20. So that way I'm not missing any, I don't have to do any additional if and else statements here. At the end, we check if the current is not equal to what I started with, that's this, that means there has been a change in between, and that's when I do swap. So I pass in the array, I pass in the current, and I pass in I, and I don't think I need to show you the swap function. And then I again heapify it, I again pass in the array iteratively, or recursively, sorry. I again call the function recursively, and then I say I want to pass in the new current, n is going to remain the same, and array is going to remain as it is. And that's my Heapify function. Now this is my Heapify function, so let's run through this. I start to 20, then I go to, and let me put this Heapify function over here, let me put this over here. So alright, so now I start with 20. I say that alright, 20 is, so I go in here, I start with the for loop, I is equal to, so let me put this, let's try to overwrite these. So I say I is equal to 4 right now. So I times 2, that is 4 2s are 8 plus 1 9. So we have 0 1 2 3 4 5 6 7 8 9. So I have that, and right is 10. So left is 9 and right is 10. And then we check what's the left state here. So right now left is 9 and right is 10. So what's the state here? So current right now is 4, and we have 4, and then I compare that with, is 9 less than 10? It is. And is left, that is 10, greater than the current, which in this case is not the state. So I check here, is the statement fails here itself. 10 is not less than 10, so I just say the current and the thing has not been changed. So now I decrement it. So now I go to 3, so I go to 9. The same case again. This is 3, so I in here is 3, this is 7, and then this is 8. So these two go, this becomes 7, and this becomes 8. But now, since both the conditions pass, left is less than n and right is less than n, 7 and 8 both are less than 10. So what we do is we check the next ones, that is 3 greater than 9? No. Is a greater than 9? So now it doesn't matter, it's not going to work. So now what I do is I go to 4. Now this here is, or I go to 2. So 0, 1, 2. So I decrement it to 2. So I becomes 2 now. Actually this was 3. This was 3, but now it becomes 2. So I becomes 2, and I'm gonna change that over here since it's too much, it's repetitive. I becomes 2, left becomes 5, and right becomes 6. So I get rid of both of these. So left becomes 5 and right becomes 6. So now we have this, and what we need to do is check again. This condition satisfies, the first condition satisfies, of course, but then is the left greater than the current? So is 44 greater than 4? Yeah, it is. So my current now changes to 5, or not this, the current changes to 5, and what happens is I go here. Since this condition still satisfies, the right's not going to change, but the current is a bit different. So is 11 greater than 44, which is not the case. So we come here and we see, alright, the current is 5 and I is 2, so it's not the same. So what we do is we swap. So we swap these two elements. So this becomes 44, and this becomes 4. So here what we do is, here as well we swap. So we have this array over here, and we have this over here. So we are going to put 4 in here, and we are going to put 44 in here. So as you can see, there is a swap in the middle. So now what we do is we go iteratively to the next one. So my current is now 5, so I pass in 5, n is as it is 10, and array. So now I recursively call 5, Heapify. I recursively call Heapify, and I insert the I is going to be 5. So I get rid of this. This here is 5. I get rid of these two, and this here is 11 and 12. Well, clearly those two are completely out of bounds because the size of the whole thing is 12. It's 10. Sorry, it's 10. So we return back to our previous call, and since there was nothing called after that, so we return back to our previous caller, that's here, and now I becomes 1, so I come here. Since here both the children are small, I go at the top. Again, none of these two work, so I go back at the top. Now it's 10, I'm at root, and as you can see, we have 0, that is the current I, or current is 0. We have 1 and 2, and then we can see that left is greater than the current, so 52 is greater than is greater than 10, so we swap it. We get rid of this and we get rid of this, and we write, and 52 is still greater than 44, so of course this condition is going to work, but this condition is not going to work, so the current's not going to be the same, so we swap that. And now we have 52 at the top, and we have 10 over here. Now we go here, and when we see, alright, the current is the next one, that is 10, is there a swap that we need to do, that we need to perform? And again we go here, and yes, we do need to perform a swap over here because 20 is greater than 10, so we again perform a swap. That goes over, that gets rid of these two, so we have 20 on here and we have 10 on here, and then again we know that the current has shifted, so we come here, and then we see, is there a swap that needs to be taken place over here? And there is, because again, once we replace 10, when we swap 10 with 20, now 10 is smaller than 12, so again we do a swap over here, and as you can see, we get rid of these two, and we have 12 over here, and then we have 10 over here, and there is nowhere else to go from here, so we just return back to our previous call. And after this first iteration, what we have seen is, as we stated before, 52 is at the top. So now we have, so if we look at the original array, we have, I'm going to get rid of these, so we have 52, we have 20, we have 44, we have 9, I need to get rid of this, and we have 12, we have 4, we have 11, we have 3, 8, and then we have 10 at the end. At the end. Now what we do, now that we have, as I stated before, since we are doing the Max-Heap property, since we are carrying out a max heap, the largest element at the top, the root, at the end of this iteration is going to be the largest element in the entire heap. So what we're going to do is, we're going to take this element and we're going to swap it with the last element. So as you can see, I have written this code here. So what we're going to do is, for our next iteration, we are going to start from the second last element, that is this one, and we are going to swap it with the first element, that is this. So now what we are doing is, we are getting rid of this, and we are going to put 10 over here, and we are getting rid of this, and we are going to put 52 over here. So in our main array, this 52 is going to be replaced by 10, and it's going to be swapped actually by 10. So 52 goes here. So the last element is going to be at the end. The largest element is going to be at the end, and then we reduce the size, and then we heapify it. So we start from 0 to 9. So what we do is, we get rid of this element completely, so we don't even look at this in our heap. So in our heap, this thing is gone, but it's still there in the array. We are no longer considering it. So what we do is, we start again from 0, we compare which one is bigger. Well, if this is bigger than this, so we swap it with that. So now in here, these two are gonna get swapped. So now we have 44, and then we have 10. Now between these two are gonna get swapped, 10 and 11. So I'm gonna get rid of the whole block here. It's gonna be 11. Underneath is gonna be, let me start from here, 4, and it's gonna be 10. So now we have 44 at the start. So we have 44 at the start. We have 20. We have 11. We have 9. We have 12. We have 4. We have 10. We have 3. And we have 8. So as you can see, this is my entire array at the end of the first iteration. And as you can see, again, 44 is the largest element in the entire heap. So what I do about it, I take this and I swap it with the last element, in this case, which is 8. So I take 44, I get rid of it, I take 8, I get rid, and I swap it. I have 8 at the top, and then I have 44 at the end. Now technically I don't even need to write it over here because I'm not going to take it into consideration, but I need to write this over in here. So I have 44 at the end, and in here I have 8, and it's going to go from here. We no longer need it. So now my next one is going to be 3. So the size is 3. I start from 0 again. So I start with 8. Again, which one is bigger? 20 is bigger. So I get rid of these two. Well, technically not get rid, but I swap them. So I have this and I have 8 over here. Then I check at 8, I see which one is bigger. So now I have 9 and 12. So I swap 8 and 12. So I have 12 and then I have 8. And then again at this point there is nowhere else to go, so I just take 20 and I swap it with 3. So now 20 is, so let me rewrite this again. So before that, let me put 20 at the end. So we have 20 over here, and then the rest of it is going to be 3, 12, 11, 9, 8, 4, 10. This is not going to be there. This is not going to be at the top. That's 3. Now we repeat the same process again. So we have 3 and we have 12 and 11. Of course 12 and 3 are going to be replaced, or not replaced, swapped. The 8 wasn't replaced. Actually it's going to be swapped. So we have 12 over here, and then we have 3 over here. Again, which one is bigger? 9 and 3. 9 is bigger than 8. So we are going to do a swap between 3 and 9. So again, we are going to take this, we're going to get rid of it. We are going to have 9 at the top, and then we are going to have 3 in here. 3 in here. So now there is nowhere else to go. So we go back, we again replace 12. We swap 12 with 10. So this goes, and this comes at the top. And then at the end here we have 12. We get rid of this, and again we write this as 10, 9, 11, 3, 8, 4. So this is now my array. Now we go for another iteration, since we haven't reached 0 yet, because there are still elements in there. So I is now going to be, again we're going to start from 0 and it's going to end up to 0, 1, 2, 3, 4, 5. So we're going to stop, and I is 6 right now, so this is going to stop until this. So again 10, 9, 11. Of course these two are going to get swapped. So we start with these two and we get rid of these. By this time I think you should be able to know the way we are doing it. Again, 4 is the child of 10, 8 is the child of 9 and 3. So, sorry, 8 is the child of 9. This is the way I have written it. I think I'll just move this a bit here. Right, there you go. Now, again, at 10, there is nowhere else to go, so we just don't do anything. Again, 11 is the largest in the entire heap at this point, so we just get rid of it and put it over here. So rather than rewriting it, let's move this over here. Right. And then this thing is gonna move up at the top. So now this is a heap. We need to rewrite this. Technically we need to rewrite this, and let's say we have 4, 9, 10, 3 and 8. So between these two, 10 is the largest. Between 9 and 10, 10 is the largest, so we just swap them. And then my next level, there is nothing at 4, so just put 10 at the end and put 8 at top again, and again rewrite the whole damn thing. Not bad. Just rewrite the whole damn thing. We have 8, we have 9, we have 4 and we have 3. So 8 and 9, well, 9 and 4, 9 is bigger, and so we just swap these two. Now again, 8 and 3, of course there is nowhere else to swap, so 9 is the biggest one, so we take 9 and we put it at the end, and we swap it with 3 here, and this also changes. So now we no longer have that, but instead we have 3, 8 and 4. Now again do the same exact thing, 3 and 8 and 4. Again 8 is the largest, so we swap it with that. We put 8 at the top, and then 3 comes here. There is nowhere else to go. We go back and then we say, alright, 8 is the largest, so we swap it with the last element, that's 4. So that means we put 8 again on the stack, so there is nowhere else to go, because we are just going to reduce the size, and we swap it with that. So what happens now? 4 is the largest. Well, before that we need to rewrite this. So we have 4 and 3, and basically we're just going to swap between those two. 4 is the largest, so we're going to put 4 back, and then 3 remains. So basically the whole stack is empty now, and we need to rewrite this. So we have 4 here, and well, I'll still write 3. So 3 is the only one that's remaining, and there is nowhere else to go, so we just, that's it, the whole array is now sorted. So we take 3, take 3 and I put it over here. So now as you can see, the whole array has been sorted, and this is how you use a Max-Heap property to just sort the entire thing. Now if we rerun this, we can see that we can also use, if we use the min-heap property, all you need to do is change this to the other side. So all we need to do is take this, and in here put this. There it is, and I put it over here. So that's it. Once you do that, whenever the top one is, whenever you have something along this lines, 5, or let me put it here. We have 5, 10 and then 3. All it's going to do is going to go here, is going to check, is left smaller than, is left smaller than the current? No. Is the right smaller than the current? Right. So then you swap it. So at the end of the iteration, you'll have the top one is going to be the smallest one in the entire heap. All you need to do is replace it, swap it with the last one, and you'll find the last one being the smallest and the first one being the largest. That's all you have to do. Or you don't even have to do the min heap, just do one of the heaps and then just read the array in the other way, in the other direction. So here if you read the array from right to left, you're going to get it in ascending order. If you read the array from left to right, it's ascending order, so on and so forth. So it's up to you how you want to use, which heap you want to use, like heap method you want to use, whether you want to use the min heap or whether you want to use the max heap. It's all up to you. So now that we have seen, let's take a look at the code that we have written and then run it and execute it. So now that we have seen how the entire heap sort works, let's take a look at the implementation of it. So as you can see, I have implemented both recursive and non-recursive versions. So for the recursive one, we first iterate through, as we saw before, we take the second last level of the tree and we take the node that has children in it, and then we check if we send that thing to the Heapify function. So we pass in the array, we pass in the index that we are and the size of the whole array at that point. And then as we see here in the recursive function, we take the current index, that's the start, then we take the left child and the right child, and then we do a comparison check whether the left child or the right child are within the bounds of the given array, and if they are, we check if the current of the left child is, in this case I have implemented min heap, so we check that if the parent is greater than the children. If it is, we take the smallest of the children and then we set that to the current, and then at the end we check if our current has changed from what we began with, and if it has, then we do the swap and we recursively call the next state. That is, we go to that child and check if it has children. If it doesn't have children, it's just going to return, and the current's not going to change, so it's just going to return. And since there is nothing afterwards, we just return back to the previous call that's here. So once that's done, we go to the second for loop, which starts from the second last node. As you see, we do the swap here. We swap the root with the last element, and then we decrease the size. So now we start from the top again, and then we see which of the root or which of the children are the smallest, and then we swap them and then we continue. As I stated in min heap, after this iteration, after this iterating through this loop, the first element in the heap, the root element of the heap, is going to be the smallest element in the entire heap, and that's because this is the min heap. So we swap it at the end, we put that element at the end, and we take the last element, swap it to the first, we decrease the size of the heap, and then we repeat the process till we are done with the entire heap. So this is how recursive element works. This is how recursive algorithm works, recursive heap sort. Now if you look at the non-recursive one, the only difference is that instead of giving a recursive call, what we do is we change the start in this case. So we have a while loop which states that if the left child is out of bounds of the entire is over the limit or over the index, the last index, that means my current or my start index is the leaf node. Because, and if let's say if current is 9, index 9, and if the size of the whole thing is 10, so the current times 2, that's 18, plus 1 is 19, is definitely going to be less than 10. So as we see here, my left child is out of bounds and there is no point in going over there because there is nothing there. I'm clearly at the leaf. So what we do is, let's say if you are not at the heap or at the leaf, and what we do is we take the left child and the right child, then we check, it's the same exact check, we check if we are within bounds, and if my current, and now here I'm implementing max heap. So as you can see, I'm checking if my current, the parent, is smaller than one of its children, and if that's not the case, I'm checking which is the largest children. And once that's done, we check whether the current index and the start index are different. If they are different, that means one of the children is greater than the parent, and then we do the swap. That's the same exact state, but instead of giving a recursive call over here as we did below where we gave a recursive call, what we do here is we just change the start. We set the current as start, and then we set the start as current, and then we repeat the process. And again, you don't have to keep track of the parent because we don't have to keep track of which way you came, unlike in recursion where it keeps track of it by default. Here you do not have to do it because again, after the recursive call, we are not doing anything to it, so there is no point for us to keep track of it. If we were doing something after the recursive call, then yes, we might have been forced to keep track of what nodes we visit along the way. But here, since we are not doing it, there is no point for us to do it. Now, if the current and the start are the same, so none of the children are greater than the parent, then I just break the while loop. So we just return back to our previous call, so that's here, and the same thing happens. So the non-recursive heap sort, this method does not change, it's basically the same. The only thing change is this Heapify non-recursive method, and as you see, we are using a while loop here, and this is more of a for loop. So this is a for loop, these remains the same, and this is just a while loop that goes on until one of the condition is met. So either there is no change or we have reached the end of the tree or the last level of the tree. So this is how both the functions work. There's one more thing I want to go over here is is this copy function, which acts as a deep copy rather than a shallow copy. So we'll explain that later. Well, let's complete this. So if we run this, as you can see, this is array 1 and this is array 2, and the recursive one, as we stated before, uses min heap. So clearly the ordering is in decreasing order, so the first number is the largest and the last number is the smallest, whereas the non-recursive one, the array 2, is done using max heap. So the first element is the smallest element and the last element is the largest element. So as you can see, if you want to do it in a decreasing, if you want to sort an array in a decreasing order, all you need to do is use min heap, and if you want to sort the array in an increasing order, all you need to do is max heap. So said that, let's take a look at the copy function here for a second. Now, as you can see, when I do a copy of this, what I do is there are two kinds of copies in Java. So let's say if I just write this, and if instead of doing a copy, I just say, now this is technically correct, but what this does is, let me draw this out. Let's say I have this function, let's say I have this index over here, and this is my array 1. So this points at array 1. Now when I do this, what this does is it creates a new variable called array2, and instead of creating a copy of it, it just points back. This thing is just going to point to this place. So now both of them are pointing at the same place. So that's why I wrote the copy function called copy1, because now, as you can see, I'm actually iterating through the whole array. I have created this temporary array and I'm creating a copy of this array, a hard copy, rather than just pointing references to the same address space. So in this case, what happens is when I do a copy function, it creates a new array, of the same size, and instead of copying over here, what this does is it points towards this, and the elements are exactly copied according to their indexes. So if I look at this, now I have to do some changes. If I run this again, I saved it, but again, as you can see, they have already been changed. Let me rerun this. Instead of printing array2 over here, let me print array2 after array1. So if I print this over here and if I run this again, as you can see, printing array2 recursive heap. Okay, I'm gonna get rid of this. So I'm gonna get rid of this and I'm gonna rerun this. So we have array1, we have the recursive heap sort print array, and the array2, as I stated, is also recursively printed, or is also sorted. So as you can see, if we just assign it, all we're gonna do is just create a new variable that points to the same memory space. Whereas if we do a copy of this, so let's do a copy of this. Now we're going to do is we are going to create a copy, and as you can see, array2 is exactly a copy of array1, and even though we have sorted array1, array2 has not been changed, and here we sort array2 again. So this is one of the small examples of how you wanna just something that I saw, or something you want to keep track of, where if you want to copy two arrays, make sure that you create a copy function rather than just assigning it, because then you will be assigning the same variables, or assigning to the same address space, two variables to the same address space. So that's the whole function, that's the whole algorithm for it. You can find the link to the algorithm, to the implementation, in the description below. And if you have any inputs, leave them in the comment section, and I'll hopefully see you guys in the next video. So if you like the video, please share and comment